Think, pair, share. First, you're going to use the concavity test to find the intervals of concavity for the function g, and then identify any inflection points. I'm going to pause the video right now, and I want you to try these problems. When we come back on, I'll have it worked out already, and I'll talk through highlighting some of the major points. All right, so first we're going to find the second derivative. We love taking the derivatives of polynomial functions using power rule. My second derivative is this line, 6x. We then need to find out where that second derivative is 0 or undefined. There are no domain restrictions for that, so it's always defined. Where is it 0? It's 0 when x equals 0. So that divides up my domain into minus infinity to 0 and 0 to infinity. There's only one of two choices for x values in the pink interval. They're either going to be, the second derivative is either going to be positive or negative, and for x values in the green interval, the second derivative is either going to be positive or negative. So we're going to go ahead and do a sign test on the second derivative. Now this might seem like overkill because you do know g double prime is a line, y equals 6x. Pretty steep slope there. I think it's also reasonable to just say, oh my goodness, y equals 6x is positive when x is positive, and it's negative when x is negative. But just to model the structure that we've been doing, I've gone ahead and done the sign test on the second derivative with a table of values. But this is perfectly fine for a justification for me. You can see pretty quickly where the second derivative is positive or negative. So I've gone ahead and summarized that result. And right here, since we're changing in concave, all right, so since my concavity of g is changing from concave down to concave up when x is 0, 0 comma go plug in 0 into g is an inflection point, and g, 0 minus 0 plus 2, the y coordinate is 2.